So we determined that the FM piece of the radio stations that you guys listen to refers to frequency modulation. You will not be tested on this. This is one of those little things that you hear that you tuck in the back of your brain so that you can act smart when you're in the know.
Okay.
So anyway, so that leads us to, and I think we talked about with the frequency modulation, what was the radio station somebody mentioned? 92.3. Okay, that's megahertz. That's 1,000,000. Okay, so radio stations, they broadcast within a couple of thousand of hertz on either side of that, and that's where the modulation comes. Okay, where they change the frequency to get the information across. What do you think AM might stand for? Now remember, we're speaking of waves, so something. Right, but we're speaking about waves. And we use frequency for one of them. What are some other components of a wave? Approximately is not even close. Okay, if I were to draw a transverse wave up on the board, you don't even know what that means. That's not true. What is this or this a measure of? Amplitude. So with AM radio, they use amplitude modulation, which means they vary the amplitude to get the information across. Okay. And again, this is a transverse wave. What was the other type of wave? What's that? No. Of the different types of waves, there's a transverse wave in which the particles move perpendicular to the direction of the energy transfer. Remember, that's the point of what waves do. They transfer energy from one place to another. Is this ringing a bell at all? Have you been introduced to this at all? It looks like many of you have not. Some of you have. Okay, well, in a transverse wave, the particles move perpendicular to the direction of the energy travel. No one apparently knows the other name of the other type of wave. The other type of wave, which is currently what I'm using to communicate with you. Well, sound is one of the, longitudinal. Exactly. Okay? And it's the same idea. Energy is still traveling in this direction. It's the same idea in the sense that there's an amplitude, believe it or not, okay? And what that refers to is the distance that the particles are traveling in that direction. So in a longitudinal wave, the particles are moving parallel to the direction of the energy travel, whereas in a transverse wave, the particles are moving, as I said, perpendicularly. Okay? So just to give you guys something to hang your hats on this. What letter is that? And how are those components arranged? Perpendicularly. And what do we have here? Two L's that are arranged horizontally to each other. So I'm just trying to help give you guys little things. So once again, when you're in the know. Okay. So, do we notice why this equation and this equation refer to exactly the same thing? I don't know if we ever had the discussion. Remember how I was kind of acting confused? How could one equation mean the same thing? When one of them is the product of, or the result of a quotient, the other one is a result of a product. how are these two, how could they be the same thing? When in one case you're dividing, in the other case you're multiplying. The information's up there.
Like one of the products is a fraction or something. If you're multiplying by a fraction of the
In this one you mean?
Yeah.
Because of this right there. Is that what you meant?
Yeah.
So the time is in the denominator, just like it is over here. You guys see that? So they're the same thing. They just look different. Okay. And I gave you that value. We talked about nu. We talked about lambda. We all good there? Okay. I guess this is going to come later. Okay, so number 4. The common characteristics shown by X-rays, visible light, infrared radiation, and radio waves is that they all have the same, I think almost all of you put speed. Yes? Okay? Okay. Okay, the speed of electromagnetic radiation in a vacuum is a constant. It's always this. Okay? So no matter what type of wave you have, no matter what type of electromagnetic radiation you have, it all has the same speed. Okay? What does vary? The frequency and the wavelength. Oh, by the way, there is something I forgot to do. So clearly we could rearrange this equation and solve for any of those variables, right? So if we wanted to solve for frequency, clearly we would have C over lambda. Would you guys agree? And if I wanted to solve for lambda, or sorry about that, it would be C over nu. So from now on, if I happen to run into you guys in the hallway or Meyer or walking downtown upstairs or down in downtown Delaware, I could say to Ryan, "Hey Ryan, what's new?" And Ryan's going to reply with C over lambda.
I would run away from you.
Right? Okay. See, I've done that before. I've run into people in various places. Hey, what's new? C over lambda. You guys good? All right. And Kirsten see, there's two types of students I've noticed. There's the Kirsten type, who I already heard what she said, so this is where it reminded me of this. And then there's the, I don't know, no, Cameron for sure. So Cameron, let's say you and I are wandering around Meyer, we happen to see each other. Would you avoid me, or would you say hey? You'd say hey. Kirsten would, on the other hand, run away. Go find a place to hide. Everybody falls into one of those two categories. Have you really? I do that when I see Mr. West. I'm
no idea.
Fair enough.
I'll see him and I'll walk through the right because I'm actually you can see.
Okay. Moving on. So, here we go. Number 4, 5. We're on 5 now?
Yeah.
All right, now, number 5. As we talked about, most students mess up on number 1, which most of you did, okay? The other one that is most frequently missed, get it? Most frequently missed, is number 5. Because that one actually made you take 2 or 3 different ideas and combine them to come up with the right answer. So, red light has a longer wavelength than blue light. So, and I'm speaking in terms of a transverse wave here, just because it's easier to demonstrate. Does anyone remember what wavelength, what that refers to? Well, we'll have an opportunity in a demonstration to talk about that here in a second. Or one point on a wave to the same point on the next wave. Doesn't have to be crest to crest, trough to trough. Could be anywhere. Okay. So, for example, I could measure wavelength from, somebody said crest to crest, right? Or I could measure it from here to here. Or I could measure it from here to here. It's all the same, right? Okay. So anyway, does this have a, well, how would you, this wavelength is greater than this wavelength, and assuming that these are occurring in 1 second, what else is different? The frequency. And how is the frequency different than, so we said this has a smaller wavelength. Do you guys agree? What happens to its frequency? It's greater, which would mean then that frequency and wavelength would be related how? Indirectly or inversely related, which is clearly seen in the equation, right? Okay, so there's an indirect or inverse relationship between frequency and wavelength. All right, moving on. So, with that being said, red light has a longer wavelength than blue light. There it is. Compared to the blue line on the hydrogen spectrum, the red line would represent, well, would it represent lower frequency? Yeah, so we can eliminate two of those right off the bat, can't we? Which would be B and C. Yes? B and C are gone. What about the energy piece? Well, let's demonstrate. I need a volunteer. Be careful what you wish for. Okay. We're going to demonstrate. All right. What I want you to do, you actually have to actively participate, sort of, is grab onto that. Good job. Usually I get students that see that little loop and they put their finger in there, in which case I say, you don't like that finger, do you? Because it's going to go away here in a second. Hang on. No. Grab here. Okay? And you're going to have to hang on tight. You're going to go way down there, as far as you can go. Do not let go. Keep going. Good, right there. Do not let go. Okay, you're going to have to hang on tight. Now, what is the purpose of a wave? What does a wave do? I've already mentioned it like 3 times today. Transfers energy, right? And for like a sound wave, a mechanical wave like this spring here, needs a medium. Clearly, what is the medium that we're going to use here? The spring. Okay, in a sound wave, what's the medium? Air. Okay, so that's another example of how you know air actually is stuff, because it's allowing the sound waves to get to you. I'm going to make Ryan's hands move. Watch this. Move. Dang it. Didn't work. Let me try it again. Move. Darn it. Oh, there it worked. Why could I get his hand to move from here? Because I used the spring, the medium, to transfer energy. So I applied energy to the spring. That energy got transferred to Ryan. Would you guys agree? So somehow or other we know that there's energy involved in this whole wave thing, right? Okay, so now what I'm going to do, you guys may or may not, apparently not everyone studied waves when you're in physical science. So I'm going to make what we call a standing wave, which is just a repeating pattern, okay? Hang on and try not to let your hands move. I mean, they're going to, but try not to let them move. Okay, I'm going to produce a standing wave. Okay, so there we go. Now, just for fun, oh shoot, I got a node right in front of camera. I want you to turn around. I'm going to change this a little bit because I've got a node right in front of you. everyone see that piece of masking tape that's right in front of Cameron? Okay, let me change my wave here a little bit. Okay, so now, what direction is that piece of masking tape moving relative to the direction of the energy? It's going what? Up and down, right? Whereas the energy is traveling Ryan, remember that whole thing I said about keeping your hand still? Yeah, let's quit being a freshman boy, okay? Right. All right, now, how many waves currently are being generated? One and a half. Would you agree? If you look at it, remember we just got done saying how to measure wavelengths from one point of the wave to the same point on the next wave. I had 1.5 waves in there. You guys were counting crests and troughs. We're trying. Your heads are going like this. But now, what I'm going to do, let me go back to the original wave that I had. Do you guys know what a node is on a wave? You guys didn't even cover any of this stuff. Gosh, dang it. Who's going to teach all the chemistry from now on? Because I can't anymore. I'm going to teach physical science all the time. I'm assuming you guys know these things when you walk in here. Apparently not. Get it? Node. Okay, moving on. So, a node is a spot in the wave that appears to be not undergoing any motion. So, for example, in front of Cameron, what is that little piece of tape doing for the most part? If Ryan would quit moving his hands, it would work better. Don't. Okay, I had a girl do this yesterday who was doing way better than you. Okay, so anyway, now what I'm going to do is increase the frequency. Tell me what happens to the wavelength. Wait, I got to stop. Okay, here we go. Now, Ryan, is this a higher frequency? Yes or no than it was before? Okay, let's increase the frequency again. Did I increase the frequency again? I can't maintain that very long. Ryan, what did you notice when the frequency increased? Why is that? What's that? Boom. There you go. And there's the next thing I want to do. Okay, walk towards me. Don't let go. How your hands feel? Pretty tired? All right. So if I decrease the wavelength, the frequency increased. So we clearly saw a demonstration of that. The other thing that Ryan noticed was when I increased the frequency, the other property that changed was the energy. So how were the energy and the frequency related? Directly related, right? And as it turns out, there's an equation that relates those things. In this equation, what's the constant? The C, okay? Doesn't matter which way I write it, the wavelength and the frequency are directly proportional, or indirectly proportional, right? There's also a constant when we show the relationship between energy and frequency. I left it out for a second, but I just wanted to show you the direct relationship between energy and frequency. And then there is a constant that I'm going to throw in there. That constant is indicated with a letter H. You may or may not, I can't remember if this is in your reading or not. Does anyone remember seeing this equation? You may not. I think it's in there, but you probably skipped right over it because you had no idea what it meant. Okay, so clearly the E, as everyone knows, stands for energy, and you all know that energy is measured in joules. Okay. Nu, we already know, is frequency, and that's measured in 1/1 second, or hertz, right? Would anyone like to take a stab as to what the units for H would be, and also possibly provide a means of explaining why that has to be true? Oh, no. No. The units for H. I see what you did. No, the units for H. Okay, so all we have to do is rearrange and solve for H and find out what the units are that are left over. Just like when we rearranged and solved for C, what were the units that we got? Meters per second. So that's what the C is measured in, the constant for... Now, you guys just happen to know that speed is unit or meters per second, but that's how you figure out what the constants for or the units for a constant are. So if we rearrange this equation and solve for H, what are the units I'm going to be left with? Go ahead. No. Well, yes, but I never wrote hertz up here. A joule what? No, not joules over second. Because if you think about it, this is joules, right? And this is 1 over 1 second. So it's a joule second. Yes, Charcy is here. Yeah, he is. Oh, okay. Oh, okay. Yep. Where'd you go? You moved. So, did you show up late for first period? Oh. Okay. Moving on. So does everyone see what happened there? So let me give you the value for that also. There is a value that goes with that. Just like there's a value for C, there's a value for H. H is called Planck's constant, and this is not Mrs. Planck that works in the athletic department. You know, I don't even know who that is. Anyway, it has the value of 6.626 times 10 to the negative 34th joule seconds. So anytime you use H, or Planck's constant, it's 6.626 times 10 to the negative 34th joule seconds. All right. Anyway, I think we can clearly see that energy and frequency are directly related. Now, though, we get the fun part of combining the two equations. Because depending on which type of waves you're studying, what types of equipment you have available, sometimes it's easier to measure frequency, sometimes it's easier to measure wavelength. So, if we combine these two equations, and recognizing that nu is this, we could write E equals hc over lambda. So what's another way of writing that? Because what's new, Cameron? Excellent. And so there we go. So E equals hc over lambda. So, energy is directly related to frequency, but it is indirectly related to wavelength, which makes sense from all the other things that we've been doing. How many of you have taken physics? Right, everybody raise your hands because you're currently taking physics. This is what we're doing right now. So, okay, next, I'm going to take you back to something that I did with you at the very beginning of the year. Might have been the second or third day. Definitely within the first week. I had you guys, when I was teaching, well, it was in the significant figures piece, but it was also with how to use your calculators with scientific notation. Do you guys vaguely remember that? Yeah. And two, the other thing I was trying to emphasize was learning how to estimate answers. So to one significant figure, what is the result of this calculation? I actually gave you this very similar. You may or may not remember this. I gave you a very similar question. And I'm not asking you to do this right now, but if you looked back in your notes in that first week or so, I think you would find something incredibly similar to this. So anyway, to one significant figure, what would be the result of this? I probably better do this. Okay. Now, I think I got it. I have the single digit. Anyone have a single digit that you'd like to throw out there? What do you got? What's that?
5.
I came up with 5. Are the rest of you coming up with 5? You're sitting there going, what? Now, here's the harder part. What did you get for the exponent? 19th? All right, anybody get anywhere close to that? I was thinking negative 16th. But again, I did it fairly quickly too. Okay, here's how I got the 5. I don't know how Josh got the 5, but here's how I did it. I rounded this to 3, this to 7. 3 times 7, 21. 21 divided by 41. Right around 5. Wouldn't you guys agree? 21 divided by 41? No? Not 5? Sorry about that, 0.5. 0.5.
Oh.
Right, would you guys agree with that? Sorry about that. I did some other math. Okay, so anyway, so we're looking at approximately 0.5. Now I dealt with the exponents. Did you do it in that order also? Did you get this value first and then dealt with the exponents? Oh, okay. Everybody does it differently, okay? So now we got to deal with the exponents. This value is in the denominator of a term that's in the denominator, which means it's also considered to be in the numerator. So what do you do with exponents that are both in the numerator when you're multiplying them? You add them. So 9 plus 8 is 17. 17 plus minus 34 is minus 17, right? But then we've got this thing, which is to the 10 to the second, Oh, you might be right. I went the wrong way. So that's going to make it minus, what did we say we were at? Minus 17. That's going to make it minus 19, right? But then it's 0.5, so actually it's 20. So 5 times minus to the negative 20.